Good morning, everyone. Welcome to Chemistry with Professor John. All right, we are continuing with alkenes today, starting with easy nomenclature. All right. Now, if we have a double bond with especially hydrogens, it's easy to recognize by looking at either the two hydrogens or the two methyl. If they're on the same side, we call this a cis. Okay? If they're opposite, we call it a trans. So that's the original cis-trans idea. Now, what if we don't have the hydrogen to compare? Like in this case, so we follow the Kant-Ingold-Prelog, that the same rule that we prioritize the substituents for chirality for R versus S. So based on atomic numbers. So in this case, for each carbon, at each carbon of the double bond, we prioritize which one is higher. Okay, for example, bromine and chlorine, bromo and chloro, bromo is higher, so I'm circling bromo because atomic number 35. Versus this one, 17. Okay, that's the atomic number 17. Now, on the second carbon, we are picking methyl because carbon, atomic number 6, and versus hydrogen. So we all know methyl is higher than hydrogens. Okay, so by looking at those two, we call that a cis. Two higher substituents or branches on the same side, we call that a cis. Now, with the new nomenclature, we call that a Z. So cis is the same as Z. And then this one, we call that a trans or E. All right? So that's the idea. Now, you look at this one. Okay, you look at this one, at first it looked like a trans, right? But it's actually a cis or a Z. All right? And then obviously when you name this, you would number 1, 2, 3, 4. 2, 3, 1, 2, 3, 4. Okay, so there will be a Z. I think this is a typo. It should be 2 bromo, 2 butene. Okay, that's better because it's closer for bromo. Okay, and here you would go 1, 2, 3, 4, 5, 6, 7, 8. So you got 3, 5 octadiene. Now, how come 3 is a Z and 5 is a E? Z means cis, E means trans. Okay, now if you look at the 3, the bromo is higher, and then you look at the 4, the carbon part right here is higher. So they are the same side because on the other one, it's just a hydrogens. Okay, so that make it a cis, which is a Z. Then you look at the 5, If you put in the hydrogens, a lot easier to see. Okay, and then you can see they're opposite, so that's a trans. You can, if that's hydrogen, it's easier to look at the hydrogens. Okay, in terms of stability, okay, what are these about, right? Cis strengths. Okay, in general, the trans is more stable. The trans is more stable than the cis, and the more branches with respect to the double bond, the more branches with respect to the double bond, the more stable. So you can see higher energy mean less stable. Okay, so the number one is the least stable because is the double bond is at the terminal, so there's barely any branches. Okay, however, 3 is the most stable because it's internal double bond with all 4 branches, and meaning all the branches have atom with orbital, and the electron from the pi bond can be shared, can be spread out, make it more stable. That's one reason. Um, the way to measure that is you take the alkene and then you react with hydrogens, cohydrogenations. The one that releases the most energy, this one is the one that releases the most energy, which is the most exothermic. That's the one that has the most energy, okay, internal energy. Okay, cycloalkene, just like alkene is a cyclic, so we call it a cyclo, like cyclohexene, so on and so forth. Cyclopentene, these are special one. Most of the cyclos are automatically cis. You can tell by the hydrogens, unless it's 8 carbons or more. Like this one, 8 carbons or more. It can be cis, or it can also be trans. Okay, because it's big enough to be flexible to bend. All right. Okay. When we have the bicyclic. Now, if remember, respect to the double bond, there's p orbital overlap. That's create a pi bond, and so that's make a double bond. So geometrically, it has to be possible to do that, meaning the double bond has to be flat, and then there's a p orbital perpendicular to the plane of the double bond. The in this case it's okay, but in this case it's not okay because this one right here is on the way, it's in the way. Okay, and then you get to this one, it's okay, but this one is that's in the way. Okay, so at the bridgehead carbon, so it's not okay. I mean, there's no space for the p orbital overlap, and that's not allowed. That's known as the unstable ones, are the one that's known to be Brett's rule violators. Okay. However, if you have a lot of carbons that allow the flexibility for those to bend out the way to make space for the p orbital overlap. Okay, so in this case, obviously this is the violator, mean unstable. And this one too is unstable because this one is similar to that one right there. That's similar to that one right there. Okay, too tight, not enough space for the p orbit overlap. Okay, and you guys can try more. Example here, it's pretty good. These are all good degree of saturation calculations. Yep, like this one is nice. This one, CaH10 and 4O2. Let me show you real quick. Oxygen, we don't have to worry about. Every nitrogen, we need a hydrogen. So you can think about taking away N4H4. You take away N4H4, then you got 6, right? So you end up with 6, but now if you have 8 carbon, you multiply that 2n plus 2, 2 times 8 plus 2, so we're supposed to have 18. However, we'll have 6 divided by 2. That's 12 divided by 2. We got 6 degree of saturation. Okay, the second one's really cool. It's C14H9Cl5. Chlorine is the same as single bond, so it's the same as hydrogen. So we can combine these two to make it a 14. Now, if we have 14 carbon, if we take 14 times 2 plus 2, that will be 30. And then minus 14 divided by 2, that's 16 divided by 2, that's 8 DOU. Every time you have more than 4, 4 or more, think about benzene, because benzene has 4 DOU. So if you have a benzene, that will take care of the 4 DOU. If you have 8, maybe, 8 DOU, that may be 2 benzene ring that will take care of it. So a lot of degree of saturation doesn't mean tough, doesn't mean difficult to figure out a structure. It's just aromatic compound. Okay. Real quick on alkene synthesis, and then we'll finish it up next time. Now this is kind of a review of elimination reactions. Last time we talked about the substitution reaction does not give us alkene, but elimination doesn't matter what kind, E1 or E2, it will give us alkene products. Eliminations. Eliminate hydrogens and a leaving group like Br, Cl, OTOS, for example. Iodide, okay. Leaving group. Water, cannot forget water. That's a good leaving group. For example, dehydrations. Dehydration mean eliminating a water. And hydrogens. So first of all, we have to pronate the OH to become water. That's a good leaving group. And then we eliminate the hydrogens, and water takes off. This is obviously E1. Water take off, making the cation. And then hydrogen got eliminated, and we get a double bond. So every time you see sulfuric acid with heat, that's dehydrations. Very popular set of reagents for eliminations, and Obviously, this is the most stable. Okay, and then we also have other product as well. That would be the most stable products. All right, this one has a bit of rearrangement going on here because the OH pick up the hydrogens and then take off, and then there's form a cation, and that's a secondary cation which rearrange into a tertiary cation. So that's secondary, tertiary. The tertiary cation give us two products, the most stable product and the least stable product. And then the secondary cation give us this from the secondary. The other two from the tertiary. Here's a few other example of E2 eliminations. OH can turn into water, OH2, good leaving group, but we can also connect it to a tosyl. This is tosyl chloride, and tosyl it's an excellent leaving group because it's so bulky. It's got a benzene ring with SO2, so you can do substitution or replacements with the right nucleophile. But if you use the right base, notice that base is we've got 3-methyl. That's bulky. So it's too bulky for for SN2, and so E2 is the best. If you so this is really important. If we use that, we get elimination products. So we can control this experiments, and we get the more stable product and also the less stable product. That's a mixture. So very important that we pick the right base. We don't want to pick the one that's not bulky and that's tend to go elimination, tend to go substitutions. Okay, in this case, we don't have to worry about the base because this is a tertiary, so it's gonna do elimination, and this is strong base. If it's weak one, then weak is more likely E1, right? Plus tertiary. Okay. I'm not saying secondary doesn't happen. It's just tertiary is just the best, or even secondary. Okay, but not primary. Now, the like for secondary, it's easy to undergo substitution unless we use a bulky base. If we use bulky base, like these are the example of bulky base. T-butoxide ion is the most popular one, and they always come with the cation, positive ions. For example, this one, if you use a bulky base, use that or T-butoxide, you get the alkene product. Now, CGF versus Hartmann elimination, you don't have to memorize the name, but at least know which product is more stable, therefore higher percentage. If you do bulky base, this is not bulky. There's a difference in our outcome. If it's not bulky, it can go wrap this hydrogen or that hydrogens, and the A hydrogen is better, give a more stable product. So CGF said, okay, that's a more stable product, it's a major product, 71%. And B, less stable products. Okay, But if you use a bulky base, there's no choice. It's got to go with the with the least hinder to, even though the product um, even though the product is less stable, but it's easier than this one. Okay, that's more hinder. Okay, so the base, the structure of the base is really important here. That's the conclusions. All right. And then the rest review stuff from last time. We talked about eliminations. You know, the leaving group and the hydrogens eliminated have to be exactly opposite, or stagger or anti. Any other conformations will not be good because the base is in the way of the leaving group. Okay, so here's a couple example. If we got the two phenol opposite and perfect, we got the hydrogen and the leaving group opposite, anti. We end up with a two phenol opposite, mean trans. On the other hand, if the two phenol on the same side, the hydrogen and the Br on the correct conformations, we end up with the cis. Here's a good example. Now there's a hydrogen here, but we cannot eliminate that hydrogen because it's in the way with the Br, but both heading out. Now that's why 0%. So it rather wrap the other hydrogens to give us that products, because the Br and the hydrogen have to be anti or opposite, like this in this case. Okay. So those are good exception there, just because the stereochemical requirement of the eliminations. Something to think about. If there's no stereo, there's hydrogen everywhere, then we can form the product easily. Okay. A couple more examples here for you to look at. They have to be opposite. And then finally, we don't have to eliminate hydrogen. We can eliminate two bromine to form the, as long as they anti to form the double bonds. All right, and a couple other reactions like with zinc and dehydrogenations with catalyst. Dehydrogenation, removing two hydrogens from an alkane. Okay, that's the way that industry synthesize alkene. Very effective and can get a lot of products. Okay. All right, so it's got a couple additional problem for practice. Yeah, feel free to practice those and then discuss with me. Well, thank you everyone for watching, and I'll see you in the next video. All right.